So, hi everyone, welcome to the last TCSS talk of this term. Our today's speaker is Dr. Matthew Wingate, a fellow at Fitzwilliam College and a reader at the Department of Applied Mathematics and Theoretical Physics here in Cambridge. Dr. Wingate is a theoretical physicist doing research in quantum chromodynamics, or called QCD. About quark masses and change of flavor in quarks. This talk and the Q&A session are recorded and will be published on our TCSS YouTube channel. And to the audience, please mute your microphones during the talk to avoid any echoes. Now, please welcome Dr. Matthew Wingate. Dr. Wingate, the stage is yours.
Thanks very much, Jindra, and thanks to the Society for inviting me to give a talk. It's a pleasure to tell you a bit about my research, and yeah, it's a shame we can't be in person, but I'm happy to do it remotely. The logistics of this are a little bit awkward than if we were all in the same room. So I'd like to invite you to ask sort of clarifying questions as we go along. You're a mixed audience of scientists, and so I may slip into some particle physics jargon at some point, and if I start using a term repeatedly or that doesn't make sense, then please interrupt me. I'm not sure I'll be able to keep an eye on the text chat, but maybe if Jindra would do that, then he can interrupt me, or feel free to interrupt me yourself and turn your camera on, whatever you like, I guess, with keeping in mind that it's being recorded. Yeah, but any more substantial questions, that might lead to a discussion, maybe we should leave to the end. I haven't had a chance to run through the talk, so I really don't know for sure how long it'll take. I'll try to fit within an hour comfortably, but I might get carried away here or there. But I do have a clock and things, so I know people will be getting hungry at some point. Okay, so with those preliminaries aside, I think that's all the management I have. Then I just need to share my slides. Host has disabled participant screen sharing, so maybe I need to be a co-host or somehow be able to share my slides.
Maybe try it now.
Yep, it looks good now. So let's see, this is preview. Okay, good. Okay, is that okay? I propose to leave it, well, let me see if we have the choice of full screen or not. So let's see, if I go into full screen, then I guess I could still see if anyone wants.
Yeah. Now it's full screen.
Is that better? Or
yeah.
I guess I don't mind too much. Okay, so yeah, so it's kind of a broad title. It's a big topic, of course, and I'm only going to focus on a small area. The most interesting details to me, I guess, and most relevant to some of my research. Let me see. There we go. Up and down will work. All right, so just to give you an overall picture of where we're going during the next hour or so, I want to, because it's a general audience, I want to spend the first few minutes just reviewing a few facts about quarks, and the bound states of those quarks called hadrons, and the forces that they experience. That'll be familiar to the physicists in the audience, but hopefully I'll focus on only the bits that we'll need for the rest of the talk. And that will bring everybody along, I hope. So after presenting a few facts in sort of a straightforward way, I'll discuss a few questions that are motivating research in the field, and the most interesting questions to me and to the research that I'm doing. And then I'll discuss the difficulty that we face that my research and others helps get around. Okay, so that has to do, first, the questions have to do with the weak force, which I'll talk about momentarily, and the difficulty has to do with a strong force. Now, I want to give you a flavor for the type of work that I do, the research, and it can get quite complicated, but there's a nice toy model that I want to illustrate, spend some time talking about this because it's very illustrative and it gives a very good feel for what we do in studying the strong interactions in hadrons, the interactions of quarks in hadrons in my line of work. Now, the physics of that toy model is quite different, at least at first glance, but actually the phenomena are very similar and the mathematical methods are very similar indeed. And we steal ideas from this field to try to advance our field. So, and it's kind of fun anyway in its own right. So I'll talk about that at some length. At the end, then I'll put those things together and hopefully I'll have time to present some of the status of the current situation, combining the methods that we use with to try to answer some of those questions. Okay, so the quick introduction. So yes, of course, what are quarks is the thing that people ask if they haven't had a science module recently. So of course, you're familiar with atoms. Atoms consist of electrons in electron clouds. And so we know the modern picture of electrons is not that they're in planetary orbits, but they're somehow in some diffuse clouds. We make a measurement, they might be some average distance away from the center. But they're just in some diffuse cloud of negative charges due to the electrons. Right, and so the distance here are measured in angstroms, say, or order 10 to the minus 10 meters. Okay, so that gives you a scale for a typical atom. Now inside the atom, we know that there's a nucleus. The size of the typical nucleus is about 5 orders of magnitude smaller. Right, and so that's quite small and dense, and inside the nucleus are the protons and neutrons. But just 10 to the 5, 100,000 is a scale factor that, maybe we don't always have in our minds, able to picture in our minds. So sort of an analogy that I like to think about for the atomic scales is, well, if we take a cathedral as our atomic scale, so our electrons are orbiting the nucleus in a space about 160 meters, say, so the size of Ely Cathedral or your typical cathedral, right? That's imagine the electron cloud being that big. Well, how big do you think that the nucleus is on that same scale? Well, I would force someone to answer if I were standing in front of people, but I won't make you unmute. But if you were to guess, right, well, you can divide by 10 to the 5, I'm sure, and come up with 1.6 millimeters, right? So that's maybe the size of a small seed in a muffin. Yep. And so that's, so just a seed in a muffin would contain all the positive charge, the protons and neutrons, while the electrons in the atom would just be in some diffuse cloud anywhere in the cathedral. A main difference between that model is that, of course, the poppy seed, the seed in the muffin doesn't weigh very much, whereas the cathedral has enormous weight. But on the other hand, in this atom that's that size, all of the mass of the atom would be in the poppy seed, whereas the cathedral would be some diffuse cloud. So that's kind of interesting. Now, as I was saying, the nucleus is contained of protons and neutrons, positively charged protons and neutral neutrons. And so it's the positive charge of the proton that interacts with the negative charge of the electrons to bind the electrons into this neutral atom or isotopes or charged ions. But so there has to be a different force to overcome the propulsion of the positive charges to keep the nucleus together. And that's the strong nuclear force.
Hello?
Hello? Question?
No.
I don't hear a question, but I'll just continue. Right, so in the nucleus, we have a positive charge, right? And so positive charges repel in the electromagnetic interaction. So the strong force has to overcome that. And in fact, it has to include, an attraction for these neutral particles.
Excuse me, we have a question in the chat.
Okay.
What is the exact size of an electron?
The electron itself, we think is a fundamental particle. Nobody has ever measured any structure to the electron. So as far as we know, it's a fundamental particle with nothing inside. Yep. So that's a good question. And I will say the same statement about quarks in a moment. So, the fundamental particles that we know about, we've never probed at high enough energies to measure any size to them. That would definitely be interesting. That would be something well beyond what we understand for particle physics now. Mm-hmm. So we can't say anything about the sizes of those particles. As far as we know, they're point-like, or of course they're quantum-y. So the real statement is that we don't observe any structure. Yeah. As far as we know, they're elemental. Good question. Yes, so in fact, unlike the electron, then the protons and neutrons do have structure. In fact, decades ago in the 70s, earlier, people were colliding or shooting electrons at nuclear targets, and with enough energy that you could resolve the structure of neutrons or protons, okay, to definitely show that they were composed of particles. And those particles are now called quarks, okay? So our understanding of protons and neutrons now is that they're bound objects of three, what we call valence quarks. So three quarks that carry sort of this name called flavor and nominal electric charges, right? So the way this works is that the proton contains two up quarks and one down quark. The up quarks have a positive 2/3 charge, and the down quark has a negative charge of 1/3. So the sum of those three adds up to 1 for the proton, whereas for the neutron, we have two down quarks and one up quark. And adding those charges together, we get the neutral neutron. And the force that binds them, binds the quarks inside the protons, is just the same force that effectively binds the protons and neutrons together. Okay, and that's the strong force. And we use the sort of a prop. We use the word color as an analogy here because the force has the number 3 appearing in it. So that in order to have a bound state of 3 quarks, we need something that's color neutral, okay? Because we don't observe this color charge separately. We don't see it separately, right? All of these protons and neutrons, we don't observe color charge themselves, but we assign this sort of fictional, not fictional, but we assign this charge, which we call color, for just because of the analogy of 3s. We need 3 together. So like if you have 3 primary colors, you add them together to get something white. Okay. So that's where the word color comes in. And in analogy with quantum electrodynamics, describing the electric and magnetic forces at the quantum level, this color dynamics is called quantum chromodynamics. Okay, so that's another word for the strong force here. Okay, I'll come back to the strongness of the strong force later. But I want to make the point here that quarks, these objects that make up protons and neutrons, they feel all 4 of the fundamental forces. They're the only fundamental particles that do. So the quarks have mass, okay, so they attract gravitationally. Now that's not an interesting part of the standard model in particle physics. There are a lot of interesting questions about gravity and how that fits in with the standard model of particle physics, but in the physics that I'm studying here, gravity really plays no role. In fact, the quark masses are usually negligible here, at least for protons and neutrons. So let's leave aside gravity. Now, electromagnetism we talked about, that's what's important in atomic physics. But to some less extent, the charges of the charges of quarks aren't such a big effect in the dynamics inside protons and neutrons. it's a weaker force than the strong force. And so we don't, for the purposes of this talk, we pretty much can ignore electromagnetism. So what I want to focus on in this talk are the strong interactions and the what so-called weak interactions of the quarks. The strong interactions are the ones that bind the quarks into the bound states like protons and neutrons. Now I'll use a generic term called hadrons to describe the bound states because there are quite a few hadrons that can be produced at least for brief moments in experiments. And we'll give some names to some of those. And it's those exotic particles that decay quickly in particle detectors that give us more information about the quarks. Beyond just studying protons and neutrons. Now, we already introduced quark. I talked about up and down quarks, those types of quarks. We give another fanciful name to that sort of type, which is flavor. Okay, so obviously nobody's tasted a single quark and can't say that one tastes one way and another tastes another way. But we have to just come up with some property to assign to them. And I guess physicists in the 70s had a more, I don't know, innovation or what's the right word? They enjoyed themselves in naming some of these things more than some of their predecessors. So they're not boring names, and they lend themselves to fun puns. Okay, but so color and flavor have nothing to do with our ordinary color and flavor. But when I use color and flavor, I mean the strong interactions and the weak interactions respectively. Now the word nuclear has to do with sort of historically, these forces were seen when studying atomic nuclei. Now we know that they persist down to the quark level. So the use of the word nuclear is really only used if you might be confused. We might be talking about some other weak force, some like van der Waals force or some emergent force at larger scales. Now, coming to flavor and the weak interactions, let's talk a bit more about that. So I told you about the content of neutrons and protons, the respectively circling. So it's the weak interactions that change the flavor of those quarks from one to another. It's quite different from the strong interactions and electromagnetism and even gravity, where those three forces, persist over long amounts of time. They're the glue that holds things together, whether it's the quarks glued into hadrons or electrons bound with atomic nuclei, or planets bound to solar objects. Those are forces where you can describe long-term interactions, long-distance interactions. The weak force stands apart in that we don't talk about bound states bound due to the weak interactions. They're so weak that we really just consider single weak decays or single weak interactions, single quantum of the force being exchanged or emitted. And that's what's happening when a neutron changes to a proton inside maybe an atomic nucleus or maybe on its own. So when that happens, what's been observed is that an electron comes out. It's called a beta decay because in the early days, they didn't know it was the same particle that's orbiting an atomic nucleus. But it is in fact an electron, this beta particle. And then to conserve energy, there's another very light particle that comes out called a neutrino. I'm not really going to talk about electrons and neutrinos and their heavier cousins at all, but that they are obviously, they are a part of that decay, and they do interact weakly, but not strongly. So what's happening in a neutron decay? So what's happening inside the neutron and proton is just that a down quark is changing to an up quark. And as I said, that's being mediated by the weak force. And so we have a quantum particle that we say is emitted when the weak force acts. So now we know in our current theory how that works. So down quark will emit a W boson that propagates for a very short distance. And what remains is a U quark. And that W boson very quickly then turns into a neutrino and electron. So that's the weak force changing quark flavors. Now, there are actually more than those two quark flavors. The two quark flavors up and down are the ones that are, make up everything, every atom in the universe inside the atomic nuclei. So all protons and neutrons are just made up of up and down quarks, except for brief moments due to quantum sort of fluctuations and things. But there are actually 6 quarks in total, 6 flavors of quarks in total. These can all be created at particle physics experiments just by using Einstein's famous E = mc² relation. So if you take protons, for example, and accelerate them to very fast energies, you give them a lot of kinetic energy, bash them together, and for brief moments, that kinetic energy can be turned into mass energy for these massive states composed of more exotic flavors of quarks. Then they decay quickly, giving up their mass energy back into kinetic energy, and those processes are measured in particle detectors. So with this table, I'm just telling you some names of those 6 quarks, right? So up and down are basic names describing the constituents of protons and neutrons. Then people discovered that there were particles that didn't fit into that model of just up and down quarks. They were puzzling, so they called them strange, and so assigned a strange quark to try to describe those particles, and that worked out pretty well. Later, a 4th quark was needed and discovered, so it's got a charming name, I don't know, charm. And then indeed, there's another pair of quarks that exist, the bottom quark and the top quark. Now, as I was saying, physicists like a good pun, and maybe it's the only literary device that physicists really understand, myself included. So we have fun with puns and things. And so for the purposes of, making jokes and things, often we use more exotic names for the bottom quark and the top quark, beauty and truth. Okay, so you can have nicer conference titles with those alternate names. But I think normally we stick to the boring names, bottom and top quarks. They have the same types of charges. They're positively charged up type quarks, up, charm, and top, and negatively charged down quarks, type quarks, down, strange, and bottom. Now, the range of masses here, that I put them in natural units for particle physicists. That's in billions of electron volts divided by the speed of light squared. The units don't matter, but if you look at the relative sizes, they're really hugely disparate. And that's one of the puzzles that we have. Where does this huge mass difference come from? I mean, well, we have 2 particles that are mostly massless, very small quark masses compared to the proton mass. That's an interesting side story. The most of the mass of the proton, nearly all the mass of the proton or neutron just comes because of the dynamics, the strong dynamics of, there's actually a condensation of the quarks that gives the particles the mass. So it's in the binding of those quarks that gives the protons the mass, not the masses of the quarks. However, as you get more exotic quarks, they do gain in mass. And there's a natural division sort of between the up, down, and strange quarks, which are considered light quarks. The masses of those quarks are lighter than the proton mass, for example. And the heavier quarks, where you've got a charm quark is a bit heavier than the proton mass. The bottom quark is about 4 times, not quite 4 times that. And then this absurdly heavy top quark, which took ages to find, and has a mass almost as much as a platinum or gold atom or nucleus. So that's really difficult to understand. Now, okay, so those are the quark flavors, and they're wildly different masses. And so what we're interested in studying, as we'll see, is the changing of those flavors through the weak interactions. Yep.
We have another question in the chat. Why is the mass of the top quark unusually larger than other quarks? That's
a very good question. That's a question for open research. There's no explanation for why the top quark has the mass that it is, or in fact, any of the quark masses have the mass that they are within the standard model. So there are theories that try to treat the top quark differently, and maybe the top quark interacts or mixes with some new particles in different ways. So there are lots of theories beyond the standard model trying to explain in a natural way why the top is so different. I mean, it comes down to how they interact with the Higgs boson, the so-called scalar particle that I'll mention again in a minute, that's been discovered. But there, as far as our current understanding of the standard model is concerned, we have no idea. It's an open question, and it would be great to understand that better. Good. So yes. So oops, I keep hitting the wrong button. Okay. So in fact, there are a lot of open questions with the weak force. That's the weak force is the area of the standard model that does raise these types of questions, just like you asked. So a different question is, why is the weak force so weak? You know, as I said, we don't really have you know, particles bound by the weak force that in the same way that we do the other three forces. Well, we have an answer for that within the standard model, an answer of sorts, and that's that the other force carriers in the quantum theories, well, if in a theory of quantum gravity, there's a graviton that's exchanged. In electrodynamics, the photon, this massless photon, is what carries the weak force. Sorry, the electric force, electromagnetic force, and in QCD, in the strong interactions, we talk about a gluon. Which is the analog of the photon for the strong interactions. Those are all massless. The W boson, on the other hand, has a big mass, okay, the one we talked about. And that's unusual in the types of theories that we're using to formulate particle physics. And it requires a sort of new mechanism or a new feature of the theory, in that there's a breaking of symmetry in the theory. So that's an interesting story. I won't go into it. It's been told a lot recently in the past decade or so, because it's the story of that yields the Higgs boson that was discovered, I guess, in 2012. And so discovering that Higgs boson is evidence that this story is good, although we still think it may not be complete. Yeah, question?
Excuse me. We have. It's an interesting question. Could there be potentially more than 6 different quarks, or do we know that there are only 6 in total?
Yeah, there could be. I mean, with all these things, well, I suppose there are some things that are theoretically hard to build, but you can certainly consider a theory with, say, 8 quarks. People talk about 4th generation physics. The trouble is just that there is no experimental evidence for them yet. So you have to work with the theory to explain why you haven't yet seen evidence of them. But there are, you know, people have returned to this theory where there might be more quarks to try to explain some deviations in experiments, or to try to explain some other things. So it's certainly a theoretical possibility, but there's no experimental evidence for it at the moment. Yeah, you can cook up lots of interesting theories that could build upon the standard model, you know, extra quarks, extra forces, more heavy particles, and that's what people are doing. It's a valid line of research to try to understand some of these questions. Good. Yeah. So here I'm focusing just on what we do know so far, right, so there could be more quarks. Maybe, yeah, you could explain some things, some of these questions with them, but so far there's nothing experimentally known. Yeah, and here's the question: why are the quark masses so varied? That's something that we don't know within the context of our standard model. So, you know, maybe there's some overlying theory that has extra particles, some extra symmetry, some unification scale, some unified theory that may explain some of these features. Also, I mean, I just added 2 other things that people wonder about with the standard model, which is that we're all made up out of matter particles. you can make antimatter, anti-positrons and anti-protons, and when those things collide, they annihilate into electromagnetic radiation for the most of the time. So, but nevertheless, the universe seems to have a lot more matter than antimatter. That kind of asymmetry is something that people believe has to come from asymmetries in the particle physics models, but we don't think there's enough of this asymmetry in the current model to describe that matter and antimatter difference. And so there could be some new theories that do bring in more of the symmetry violation to explain that. So that's one motivation for looking beyond the standard model. Also, you know, I mean, it's a nice connection between this very small and the very large. People have observed for a long time now that the stars within galaxies, for example, don't rotate as they should if you only look at the luminous matter, at the starlight. If you look at their motion, you should infer that the distribution of mass is different from the distribution of the luminous matter, of the light stars that you see. And there have been some other cases where you can use, well, I don't want to go into the things too far afield, but you can infer from galaxies colliding, for example, that the distribution of light that you see is different from the distribution of mass. And so the inference is that there must be some dark matter that doesn't interact or give off electromagnetic radiation that is in the universe. But we don't know what particles make up that dark matter. There aren't candidates in the standard model. So there are reasons to expect that there's more to the standard model than the four forces that we have and the particles that we currently know about. Yeah, and a lot of it has to do with the weak force, you know, and I'm not sure exactly where I make the point. I think the point is that you know, we'll be looking for very precise measurements of how quarks change their flavor. And with great precision and by looking in good detail, the hope is that we can see some discrepancies from the standard model. And, you know, because the way that the quarks change flavor touches on many of these topics through the so-called breaking of the Higgs breaking of the gauge symmetry and the so-called Higgs mechanism, that it may be that you know, the new particles influence how quarks change their flavor. Okay, those are the open questions. Now, there's to do with the weak interaction. So we want to study the weak decays of the quarks. However, the experiments don't see quarks in a sense. They never see a free quark, and they don't deal with free quarks in their detectors. The quarks are really confined, we say, into these bound states called hadrons. So here's a nice illustration taken from an article a little while ago about a decay that I've worked on off and on throughout my career. So here, focusing on the bottom quark, okay, very much like looking at the decay of a down quark. So the bottom quark here, instead of the down quark, is decaying to an up quark, emitting a W boson and you know, the electron and antineutrino. So just the analog of that beta decay. That's what we want to learn about. We want to study the quark physics. But the experiments measure something different. The B quark is always bound with some other quark that they've called Q bar here. Okay, maybe it's a anti-down quark or a anti-up quark, or even strange. Okay, and this type of hadron that has two quarks, a quark and an antiquark, is called a meson. Okay, but we don't need to use that jargon. The experiments measure this decay of a hadron decaying to another hadron. So what needs to be understood is this intermediate picture is we need to understand all the strong physics of how the bottom quark and the lighter antiquark are bound together in order to disentangle the quark physics, the clean weak interaction physics above from the what's measured in an experiment. So that's the difficulty. I'm not an experimentalist, I'm a theorist. And so, you know, the way that we normally do calculations in the theories, in quantum theories, is sort of by what we call a perturbative expansion, which is just like a Taylor expansion you learn about in mathematics, just expanding something out about a small parameter. Okay, so for example, in electrodynamics, where the electric coupling is rather small, you can think about two electrons scattering off each other just by exchanging a single photon. Okay, that's the most important process. If you really want to calculate probabilities of scattering and things quite precisely, then you might have to add small corrections to get the correct result. You might have to consider maybe two photons are scattered from the two electrons coming by and colliding. So this is sort of what we're depicting with these so-called diagrams. There might even be processes where an electron comes along, emits a photon that it later reabsorbs, but meanwhile, it emits a second photon that the other electron absorbs and then gets a different kick in momentum or whatever. So these processes, these pictures actually have a one-to-one correspondence with terms in a sort of mathematical expansion. And so, but nevertheless, it can be, at least at the first, the simple calculations can be done by pencil and paper. And we know how to calculate these things as theorists. This kind of expansion doesn't work for strong interactions. And that's the kind of interaction we worry about, or we have to concern ourselves with in the binding of hadrons, the binding of quarks within hadrons. So the analog picture here would be the bottom quark exchanging a gluon, the quanta of the strong interactions, with a lighter quark, maybe an anti-up quark. But numerically, the strong interactions are so strong that you don't get any kind of suppression in some small parameter as you square it or multiply it. Here this goes like a small number squared, and here that goes like the small number to the fourth power. There's no such nice ordering of this expansion for strong interactions. We'd have these two diagrams that I've drawn have exactly, are equally important as far as we know. Right, so this kind of pencil and paper Taylor expansion won't work for understanding how those quarks are bound into the hadrons. So this brings me to this nice analogy that has to do, that involves strong interactions where we don't solve things sort of order by order in some perturbative expansion or some expansion about an important result and then small corrections. We have to solve everything at once. And that happens in condensed matter a lot, sort of materials, the physics of materials that you can build on a tabletop experiment. So I want to come to this toy model and make an analogy with this condensed matter system that I'm going to tell you about with the quarks. So this will take a little while, but so keep everything I told you about the quarks in mind. And this is how we're going to calculate things within the strong interactions of QCD. But let's simplify things. QCD is quite a complicated theory. And I don't want to go into the mathematics of it, as rich as it is. It's really something for specialists in physics. Let's think about something much simpler, and just magnets, okay? So you know about bar magnets. Right, so if you have two bits of magnetized iron, right, you might have a north pole and a south pole for each bit of the magnets. Now, as you bring them together, of course, they'll want to flip. The north poles repel, and so they might flip or something like that and be anti-aligned if you're just dealing with sort of refrigerator magnets or something like that, some simple magnets. But when we put them together in materials, like what's happening inside the iron. Okay, so we've got some iron block that somehow has a overall magnetic field. So it's, there are field lines pointing, coming out of the poles here, and there's a definite north and a definite south pole. So what's happening inside that material? Well, a simple picture is just that the iron is composed of a bunch of iron atoms, and those themselves are all aligned to give you a net magnetization, say in one direction. Now inside that material, you might guess that the magnets would all like to anti-align because that's what magnets do when they're free, but actually there are quantum forces that keep the atoms lined up inside that material. Okay, so now we're picturing just a bunch of little atomic magnets stuck together in a nice crystal or a nice lattice, three-dimensional lattice. I haven't drawn all 3 dimensions, and that gives us our ferromagnet, something that can hold a permanent magnetic field. Now it happens that if we heat the magnet up, though, it'll lose this magnetization. The thermal energy will disorder these things. And that's kind of what we want to study. So these magnets are, these little individual magnets, these atomic magnets are strongly interacting with each other, okay, just like the quarks strongly interact with each other. Now let's simplify things even more. So in a real magnet, these magnetic directions can, in principle, point in any direction in 3 dimensions. Let's go even simpler. Let's imagine just a world that has 2 dimensions. So just a single layer maybe of these iron atoms. And let's say that the atoms can only align in the up direction or the down direction. So there is a discrete, degree of freedom. We can represent it as a +1 or -1. That's what we often do mathematically, but I'll probably say the words up and down repeatedly to distinguish between the 2 degrees of freedom. Or you might, in the pictures, I'll show them as blue for up and yellow for down. This is a classic model, this 2-dimensional model. It's attributed to Ising. He's German, so Germans would say Ising, but I guess he did immigrate to the US, and maybe, I believe he changed his name, maybe just to accommodate his neighbors. And so, plus I came from the US, and so I can't train myself to say anything other than Ising. All right, so the Ising model is a classic simple model. It's sort of to strong interaction physics as the harmonic oscillator is to most of what you see in physics. So the block on a spring or the simple pendulum that you've been studying for years and years since GCSEs is still, this harmonic oscillator still will be a useful picture all the way, even if you go into master's or PhD in physics. It's everything boils down to harmonic oscillators in weak interaction physics anyway. So Ising model is akin to that. The best I can do outside of physics is, think about sort of simple model systems. So like the fruit fly in genetics or the mouse in medicine. So it's just the simple system that we return to time and time again to understand, what's going on and to refine our methods. Now, in studying even the Ising model, the simplest model that we can come up with that exhibits this kind of phenomena that we're going to see, it's too complicated to solve exactly, generally speaking. At least, okay, there's a caveat that you can solve the 2-dimensional Ising model using a cute trick called duality, but that's not generalizable in the same way that the numerical method I'm going to describe is. So, right, so formally what we need to do is to think about all the different ways that these various spins can be aligned, right? There will be some arrangements where some are up and some are down, and then all the different possible arrangements. So if you want to count that, if we have n, I should say magnets, spins is kind of a bit of jargon I wanted to avoid. So if we have n individual magnets, then they can each either be up or down. So you have a factor of, you have 2 ways that each spin can be aligned. That gives you 2n types of configurations or examples of microstates. That's something that grows exponentially large as we make n large, and you may want to imagine having 1,000 by 1,000 atoms. There's certainly, atoms are small, you can have a lot in a system. So it's impossible very quickly, the number of configurations that you have to consider, quickly becomes larger than the number of atoms in the universe. And the time to realistically calculate those would go beyond the age of the universe. Luckily, we don't need to consider every single configuration of these spins. We just need some important ones or some typical ones. So here, there's a nice analogy in this importance sampling business. If you think about the air molecules in the room, we can understand the thermodynamics of the gas in the room, or outside, make some predictions about weather, et cetera, if we're getting very large. But just think about the pressure and temperature of the air in the room. We don't need to worry about configurations of those positions and velocities that are very atypical. We don't have to worry that all the air molecules are going to rush to the corner of the room and leave a vacuum elsewhere in the room. So despite the myriad of possible configurations of air molecules, there's a very small subset of those configurations that are important to understand the large scale behavior of the gas in the room. And this is true of the spins as well. And we'll see that there will be some unlikely configurations of spins for some temperatures and unlikely configurations for other temperatures. Now, a trick that we use is that we don't have to model the flow of air molecules in the room. You may have to do that if you're interested in weather forecasting and watching some dynamical weather situation. But what we're interested in the Ising model and in QCD is just for a fixed set of parameters, what are the typical configurations of magnets in this case. So we don't have to worry about realistic dynamics. We just have to use any principles or any prescription for giving us these typical configurations. And it turns out that you just need some simple properties of algorithms to do that. I won't go into those properties. Yeah. Okay. But I will give you an example. So, so one example for these spins might be to just randomly create a grid of up and down magnets, right, blue or yellow magnets, and we can create a set of important configurations by visiting each of those magnets one by one. Now here's a simple algorithm called majority rule. So if we look at an individual magnet inside the lattice of magnets, then I'd mark that with a star. We can ignore whether it's been up or down, and we can look at its neighbors, its nearest neighbors. So the majority rule algorithm tells us that we can generate a new configuration, at least from this previous one, by replacing whatever spin is here, or whatever magnetization is here, by whatever the majority rule we had looking at the neighbors. So for example, if this neighbor has 3 magnets pointing down and 1 pointing up, so in the next step of the algorithm, we should just make it point down. And then we go on one by one. So if I had just take a simple 2 by 3 lattice with a randomly assigned initial magnetizations up or down, I look at the first one, I notice that its 2 neighbors, its 2 nearest neighbors, I ignore the diagonal. So its 2 nearest neighbors have a spin pointing up. So, oops, wrong way. So in this step, going from here to here, I change this from yellow to blue. Here, looking at the star, its nearest neighbors, I've got 2 pointing down, 2 yellow ones and 1 blue one. So in the next step, I will flip that to yellow. So that one's flipped to yellow, and so on. This one has 2 yellow neighbors, so it stays yellow. This one has 1 of each. So for majority rule, you may as well just flip a coin. And I guess I flipped yellow. So this one changed to yellow. This one has all yellows next to it, so it stays yellow. This one has all yellows next to it, stays yellow. And then we repeat. Okay, so we've changed the configuration from this, which had 2 blues, to this, which has 1 blue, and so on. One more step would give us yellow. And then we're sort of stuck, right? Everything is aligned to be yellow. Now, I cooked it up to be that way. This strict majority rule will align individual magnets. That's sort of inherent in the majority rule. Now that isn't probabilistic except in the case of ties. So what we're doing there is minimizing the system energy. These magnets want to align, and so we're going through and systematically aligning them with our majority rule. That's equivalent to a 0 temperature simulation where there's no thermal energy. Now, if we want to include temperature, in our simulation, then we have to go against the majority rule sometimes. And so with some probability given by this expression, we go against the majority rule. And you might have to play a bit with the exponential function to see, but if t is equal to 0, this probability is 0. It's tending towards 0, right? We divide by something very big here, so we get something very small here, and e to the 0. Sorry, I've said that backwards. We get t goes to 0 gives us e to the minus something very big, so that's e to the minus infinity almost, which is tending towards 0. So we get a probability of 0. On the other hand, if we divide by something very big, large temperatures, then we get a probability of a half. So as I said, at 0 temperature, we always go with the majority rule. And at high temperature, we basically flip a coin all the time. We go against the majority rule half the time. Now this procedure gives us typical configurations for whatever value of t we're looking at, whatever value of the temperature. And those will be different depending on the temperature. In this way, we're minimizing what's called the free energy, not the total energy. So the energy that's free, because at some finite temperature, some of the energy is just fixed up in the property of being at that temperature in the thermal energy. Good. All right, good. So I'm going to give you a little demonstration. So I've shown you the boring situation with 2×3. I just want to pick out some highlights when we look at these simple algorithms applied to large scales. So we've already talked about the colors. We'll see that in a larger grid, 100 by 100. And we're going to look at sort of some features that appear, basically sizes of blobs. All right, and so I should thank my colleague, Ron Horgan, for sharing his program with me. So I'll stop sharing that screen and I'll switch over to this simulation, which I'll get started. Nope, too big. Okay. Now, good. Let me find share screen. All right. Good. Okay, so hopefully you're seeing this. Please shout if you're not seeing a grid of 100 by 100 yellow and blue squares that are changing. So what's happening here is, well, a more sophisticated version of the algorithms that I described is being used. And so we're flashing, the algorithms going through all of the spins, and we're just seeing each step after all the spins have been updated once. Sorry, I keep saying spins, but I mean magnets. Yeah. Okay, and I've dialed in very high temperature according in the units that were being used here. So we'll see that around 2.2 interesting things will happen. Okay, so what else are we looking at? You can look at the magnetization here. That's the average magnetization. So where I assign +1 to the blue and -1 to the yellow. So you can see it's pretty close to 0. We have roughly the same number of blue and yellow magnets in these cases, which we would expect, from the algorithm that I described. At high temperatures, majority rule doesn't play any role. The other thing we might notice is that basically you can resolve the 100 by 100, right? You see pixels of 1 by 1 or 1 by a few, right? So that's something to keep your eye on, because we'll see larger blobs as we lower the temperature. So I won't do it to, let's see if I can do it, get close to 2 something. Do we start seeing at a lower temperature? I started at 6 and now we're at 3.25. You see fewer 1 by 1 grids, and you maybe start to see blocks that are more 2 by something or 3 by something. Okay, and so we talk about those spins being correlated over larger distances. Okay, maybe it's a bit more interesting, a little colder. All right, so now we're getting closer to, we're just seeing the magnets closer and closer to each other are acting together in concert over larger ranges. And we want to call those sort of blobs or sort of, there's some correlation length, we call it, over which individual spins are doing the same thing, okay, but not across the whole lattice, okay? So they're acting in bigger blocks. So what's happening is that we're lowering the temperature and we're going to get closer to what's called a critical temperature. Okay, so far the magnetization is still hovering close to 0. Maybe the fluctuations are getting bigger. The blobs are definitely getting bigger. Let's see if we can, oh, that's perfect, I think. So yeah, 2.3 is just above the critical temperature. And now the blobs are really, they're about half or a third the size of the whole lattice. Okay, so the correlation length is now getting quite large. It's almost going across half of the grid. Lots of blocks of magnets are flipping together. Okay, we're taking away a lot of the thermal energy. And so they want to be, they want to be closer together. But there's still enough thermal energy that the net magnetization is hovering around 0. Now, if I can do it without overshooting, oop, I did, it's hard. Okay, I've overshot a little bit, but now we've gone past the critical temperature and the block sizes are getting bigger, and you may notice that the magnetization is not fluctuating around 0 so much. It's definitely taking on a positive value. We've happened to just randomly get more blue than yellow, and since we're below the critical temperature, that's going to persist. Nevertheless, we still see some patches of yellows coming in and out of existence, and they're a bit bigger than 1 by 1, many of them. Some are 1 by 1. But if we go lower, then we'll get rid of those larger islands. There's less thermal energy to go against majority rule, right? And so once we get quite low temperatures, most of the deviations from alignment are just 1 by 1 fluctuations, right? And so there you can see that sort of smoothly in between. Right, so again, even though we're in a magnetized state, here the correlation length is very small, just 1 by 1. If we get a bit bigger going back, we start to see some bigger fluctuations. Again, some bigger islands. The correlation length is getting larger from the cold side. So that's all kind of interesting and relevant to us. I'll make the connection in a moment. So I think that's everything I wanted to see from that demonstration. All right, so let me quit this so it doesn't heat the computer up too much. Let me come back to sharing my slides. Good. And here is the slide, full screen. All right, and I see I'm running out of time. So let me not repeat myself. I did take a lot of snapshots here because just in case the simulation failed. So I'll just flip through. We're again sweeping from high temperatures to lower temperatures, and you see the blob size getting bigger, where we're quite close to the critical temperature. And then one last one just above where the blob is quite big, and then below the critical temperature where now the magnetization is positive, and so on. Good. So that repeats what we've talked about. Now, I mean, I think that's interesting in its own right, this kind of phase transition. It's called a phase transition, where we go from a demagnetized state where the magnets are sort of random and there's no net magnetization, down to low temperatures where we have a persistent magnetization. Meanwhile, the correlation length goes from small to basically the whole system size, and it would be infinite in infinite volume, and then it comes back. It's a nice depiction of a second order phase transition. All right, so in the last few minutes, let me try to connect that fun diversion to what we do with quarks. So we're interested in the real world. The real world has 3 space dimensions and not 2. That's no problem. Now, we're interested in quantum theory in real time. But we have, in order to make the connection between the Ising model and lattice QCD and to use all these tricks, we do have to work in what's called imaginary time. So you take your normal time coordinate and multiply by the square root of -1, basically. It really is, like in terms of complex numbers, it's imaginary. direction, and that that does cause some problems. That means that there are some things we can't do with this method, because real time is different from imaginary time. But there are still things that we can do, in particular, looking at masses and things and things that we need for flavor physics. Okay, instead of temperature, we have a different parameter. That's the parameter governing this interaction strength. So we're not studying, in what I'm discussing, we're not discussing quarks at high temperatures, just with different interaction strengths. And instead of the +1 magnets on each site, we have quark degrees of freedom on each site. And then there's some complication that I won't discuss here. And then we have to deal with the quantum that mediates the strong force, and those are the glue degrees of freedom, basically the gluons. So there's a glue field. And then in a complication that I don't have time to elaborate on, these live not on the lattice sites, but you can imagine links connecting those lattice sites. So, so there's actually a glue field for each direction at each site, so each of the 4 directions. So that's all interesting, and those complications really do cause problems. It's what makes this a whole industry and a rich research area, rather than an exercise that you can code up in a few weeks, or and study that way. Furthermore, of course, the real world isn't a grid, right? And so I highlighted this feature about the correlation length. That's important in being able to take what we call the continuum limit and be able to say something about our discrete calculations for the real continuous world, right? And so I mentioned the differences. Actually, though, the similarities are the important things and the reasons I wanted to talk about this. So those snapshots of those magnet configurations are exactly what we do when we work with the theory of strong interactions, QCD, with lots of complications, but essentially it boils down to the same thing. We have algorithms that take some random configurations of those variables that we start with, we just guessed, and then we use this algorithm where we go by site, link by link, and we create a new guess for an important configuration, and eventually we have a bunch of snapshots of important configurations, right? Maybe one thing I didn't point out was, as I was changing the temperature, there was some transition in those simulations, right? So we're not interested in how those transitions happen, because that's not real time dynamics. That's sort of just a thermalization of what we are, of our algorithm. So we would make those changes and then wait for that to sort of come to the right temperature, sort of thermalize, we say. And that happens for lattice QCD too. But this divergence of the correlation length that we saw in the Ising model as we tuned the temperature to a critical temperature is exactly what we do when we take the lattice parameters in QCD and tune them to values that would give us continuum physics. Okay. So basically the bottom line statement is that the correlation length in lattice QCD is related to the mass of the hadron. And we want the masses of the hadrons, it's an inverse relationship. So the length associated with that mass, we need that to be getting big, just like a correlation length, compared to the spacing between sites. So we can do that in just the analogous way as what we saw in the simulation. Right, a way of talking about these blobs is to talk about correlation functions. So we just talked about blobs because we could see them, but the mathematical way that we express the blob size is to take a magnet at one point, a magnet at another point, a distance away, and multiply them together and see if they're always pointing the same direction, then +1 times +1 is always +1, -1 times -1 is always +1. So if they're always the same sign, if they're always, then we know that on average, those spins multiplied together, or those magnetizations multiplied together will always give us a +1. Whereas if they're so far apart they're not correlated, then sometimes they'll be aligned and give us a product of +1. Sometimes they'll be anti-aligned. This is a product of -1. So if you look at these kinds of as the two magnets are separated on average, are they aligned or not aligned? That tells us about the correlation length. That same thing tells us about how particles propagate in this sort of typical glue, the sea of non-perturbative glue rather than just individual gluon exchanges. So just coming to conclude this sort of analogy, right? This is sort of an artistic picture of the same decay that we showed earlier that we want to use to connect experiment to quark physics. So unlike the hand-drawn diagrams where I drew wiggly gluons here, single gluon exchanges or multiple gluon exchanges, here we've got an ensemble of typical glue fields that are important for understanding the QCD dynamics. And so those are sort of represented by these colored dots on the links for the gauge fields. And I didn't have time to tell you about how quarks and antiquarks can pop in and out of existence briefly. So those have to be accounted for. That's represented by these little circles. And then we, just like we might measure the correlation function of a magnet and an antimagnet in two different places, we can measure what happens by creating this B hadron that involves a bottom quark and some lighter quark. And and we calculate the appropriate things to have that propagate through this glue. And we might terminate it just halfway to see about the correlation length of the B hadron itself. Or we can even go in and by hand turn that B quark into something light again. So here it would be an up quark if we're changing the B to the up. All right, so we could do those things by hand, and these correlation functions that we calculate tell us how to connect to the weak physics that's being measured. All right, I think I'm going to skip the last part. It's really a bit more for the physicists, I guess, because we have some details here. There's a complication in how these things change. I just want to show some plots about the parameters that come in. So we do our calculations and experiments do their measurements. And the idea is to try to constrain these values that come into this kind of matrix formula. It tells us basically that mathematically the details of how the weak interactions allow the quarks to change flavors. But I think I'll leave that detail since we're running behind. Here are the steps laid out. Basically, my colleagues doing experiments, measure hadron decays. We and my colleagues and competitors and the whole field do lattice calculations to try to connect those things. I sort of described those. And combining the two, that tells us how to fix these parameters that are completely unknown from the standard model themselves. We do that for many types of decays. And then we ask if this standard model picture, this standard model prescription that tells us the quark flavor is governed by these V matrix elements, is that consistent? Actually, we hope that it's not, because we kind of want to discover something new. So far, the standard model has been very resilient to tons of measurements. And so, well, I think I'll leave this. These are sort of constraints that you get. And you can see that the colorful bands are measurements. And basically, typically there's allowed regions. Yeah. We do encounter puzzles. So there is an existing puzzle. But I think most people think that we've recently beat down the error bars and shrunk all these bands so that they're more and more precise. That means that we're learning more and more about VUS and VUD, these two matrix, these two quantities. But maybe there's something in our calculations or the experiments that haven't been fully accounted for. And usually that, before declaring that you've discovered something new, you have to exhaust all the other possibilities. So that's where we are there. And I won't talk about that. So yeah, I'm sorry for running over a bit, but I could stay a bit for questions. But I want to thank the organizers, Jindra and Mirka, for inviting me. Yeah, I'll just leave the takeaway points up here, but I'm happy to take questions. I'll remove that from full screen, but thanks. Somewhere I might be able to access the chat thing too, if there's, I might have to stop sharing to do that. Oh, there's the, does anyone want to ask a question, or should I,
okay.
Maybe, Jindra, if you moderate and then,
yeah.
I heard someone, I thought I heard somebody.
Hello.
Yeah, thank you for your talk. And I will. And if you have questions, then ask or write them to the chat.
Am I audible to you?
Yes, yes. Hi,
Yeah,
Nandita.
thank you. Thank you so much, Professor Wingate, for the wonderful presentation. I have a question. I will first going to frame it in a simple way, then I will elaborate a little so that you can understand what I'm actually looking for. So my question is a proton a quantum state of a positron with an electron neutrino? And the elaboration of my question is, as we know that in beta negative decay of a neutron leads to a proton, an electron antineutrino, and an electron. And in the beta positive decay of a proton leads to a neutron, an electron neutrino, and a positron. So according to QCD based descriptions of the processes in atomic nuclei finally leads to contradiction with observations. So I'm asking, can we explain our observations with quantum states of the particles like electron, positron, and the two kinds of neutrinos? Wouldn't it be worth trying to find interaction mechanism between neutrino electrons and positrons which lead to observed properties of nucleons? Could this be an alternative to the QCD theory with its inflammation need of new colored particles? I'm sorry for the long question, but this is what I'm thinking about.
Yeah, I don't think that's right. I think we know that we know that quite a lot about QCD, and it explains very well not just the the behavior of neutrons and protons, but there's a whole list of other hadrons that are created that agree well with just the basic quark model, and that's why the quark model was successful. But within percent level calculations, the hadron spectrum is pretty well known from QCD by itself. So leaving aside the weak interactions, there's electron proton scattering that tells us a lot about the structure of protons, for example. And I'm not sure that we're looking for an alternative description there. I lost a little bit which experiment you thought was disagreeing from theory. But there, you mentioned positrons, and there certainly are, you can certainly, if I'm still sharing the neutron beta decay, you could certainly have electron capture, and also the charge conjugation of this decay works, but then still that doesn't involve a positron. You can run this backwards where a proton captures an electron and turns into a neutrino plus an antineutrino. So maybe I misunderstood exactly what problem you're trying to solve. I think is I don't see what problem you're trying to solve, but I don't see where the positron is needed here, and I do see where QCD is definitely needed to describe the neutrons and protons and their excitations.
Okay. Thank you so much for your time.
Okay, thank you.
I had a question. So I've heard about the Higgs boson being a scalar, or that it's like interaction is scalar in some form versus like other gauge particles not being scalar, like having some form of vector or some kind of, I guess, tensor. I don't really know. But yeah, could you explain a bit what that means and how it changes the nature of very specific interactions?
So I think the problem boils down to understanding why the elementary particles have the masses that they do. Except for the Higgs boson, we either have spin-a-half fermions. So these are like the electron or the quarks or or composite particles. But so those are the matter particles. They have this quantum spin 1/2 property, and that's well understood. And typically the masses of those particles in theories that we work with, in particular the weak theory, are massless, and so they're naturally light. The way that they get their masses is through this so-called Higgs mechanism. That's what needs to be done to give those fermions non-negligible masses. As we discussed earlier, the values that you get from those masses take wildly valued different values, and that's because they're coupled with different strengths to this Higgs field. But at least there's some understanding about those masses, and then those masses don't contain hard to understand, well, they're relatively stable in sort of calculating them, let's say. Now, gauge bosons are, so the force carriers are gauge bosons, which, as you said, are vector particles. So they have spin 1. And those naturally have no mass, right? And that's robust. The mass is fixed to 0 in the theories. So that's good for QCD and QED. So then this again, to give the W boson a mass, we have to have some mechanism that does it. And the scale of that mass comes out naturally from this so-called symmetry breaking. So, and then after that, it's relatively robust, to calculations. Now, what happens from that is we do get this scalar particle, the only one that's an elementary scalar, and it's got to have some mass. But if you do calculations, this sort of, it's a long story, I guess, but the problem is that the calculation of that mass is sort of fine-tuned in those calculations. We have to worry about some properties of our quantum field theory that I didn't have time to talk about, but basically involve delicate cancellations. And so the terms that come into correcting this elementary scalar mass, if you were to try to look at it, in the calculation, they can get very large. And so having a mass just where it is involves some delicate cancellations in the theory. So it's sort of unstable, not unstable, but it's theoretically unpleasing. It involves what we call fine tuning. So people have thought about, maybe the Higgs mass isn't really, or the Higgs particle isn't a fundamental scalar, but maybe it's a composite particle. There's no problem with having scalars per se outside of this problem. It's just the combination of it being a scalar and being elemental. It's a little bit hard to understand why it has the mass that it has. But there are scalar hadrons, for example.
So I don't fully understand. It's probably quite complicated.
Sorry, it's a lot of jargon. And
but so can I just try So say that if it was a vector, then it would perhaps interact more with having mass in a way, or so basically by being scalar, it can alter other vectors without it itself being altered. And just big is never mind.
Yeah, well, scalars and vectors have different interaction properties. They carry, different quantum numbers, and the problem is purely theoretical. I think that there's no problem with the experiment, and there's no problem describing it. It's just sort of an uneasiness with the fact that the quantum theories that we work with have to take into account fluctuations on all length scales or all energy scales. So, the quantum vacuum is not something dead and boring, but, particles and antiparticles are popping in and out of existence all the time. And those brief moments where they exist, they can interact with, other particles around. Now, the theory tries to add up all those interactions with the vacuum, vacuum bubbles. And, as far as we know, nature is continuous, and, you can go to as small a scale as you like. But as you do that, the contributions to scalar masses get larger and larger. And so, it becomes a delicate cancellation to say that the Higgs mass is a contribution of a bunch of diagrams, if you want to order it in that way, of terms that are getting bigger and bigger when you consider these shorter and shorter distances. And so, from a numerical point of view, looking at these, you have to add and subtract, very large numbers, hundreds, millions, arbitrarily large, and get 100 out at the end. So this is the kind of fine tuning. So people have invented symmetries to say, so-called supersymmetry rather would solve this problem, because that would be a symmetry that ensured various contributions of these diagrams would come in with equal and opposite signs, and that would stabilize the mass. But we haven't found any supersymmetric particles yet in experiments. So simple extensions of the standard model like that are a bit stretched at the moment. Others are less well explored, like maybe the Higgs is not a fundamental particle, and so you can't just consider the diagrams that I mentioned. There may be more to it.
Okay, thank you very much.
Sure, it's a complicated question, but it's a good one.
Yeah.
Complicated answer.
Hello. Yes.
Hello.
Thank you for the talk. It was very interesting. So I have a question about the kind of importance sampling, which I think you mentioned on how to sort of translate the Ising model over to, lattice QCD, or generalize the ideas in the Ising model. So with the importance sampling, how can it work, seeing that I think you said earlier with the Feynman diagrams, they don't sort of decay in any nice way? There isn't a way of sort of saying these are the first order terms in your Taylor expansion or whatever. So how does the importance sampling work exactly? And are there any sort of problems related to it? Thank you.
Sure. Yeah. So the diagrammatic method is basically what we're doing. I think I sort of said it in words. What we need to calculate both in the Ising model or in quantum problems is we think we can formulate the problem in terms of integrals that we have to calculate, sums or integrals that we have to calculate, where we sum, formally we just sum over every possible microstate of the system in a statistical physics system, or we sum or integrate over all possible values of our quantum field. And from that, we can get sort of expectation values of correlation functions and all those things. So those integrals or sums involve summing over every field configuration. Now, so in those cases where we do the Taylor expansion, actually, you can approximate the integrand by a Taylor series. So then those integrals become easy because you're just doing a power series expansion, and that's what those diagrams are meant to, the Feynman diagrams are meant to show. And so you're making an approximation right away in this picture. Okay. It's a little bit, without the mathematics, it's hard to see, but basically you're throwing away many, many possible kind of interactions. Now, the connection's hard to see, I guess, because this picture is sort of in a momentum space. You're thinking of scattering and things, whereas much in the Ising model and in lattice QCD, we're thinking in position space where we have fields in real time, but those are easily related mathematically. So really in the diagrammatic way, we're just picking off just a few terms because we know that these are vastly important compared to the rest. It does get complicated if you want a lot of digits, but so in cases where in QCD where this expansion doesn't work at all, we just can't do that expansion, and so we don't make this approximation at all. We work with the full integral, but then we don't look at every single field configuration. We look at the importance sampling there. So we don't, in the lattice picture, we don't have a notion of a gluon. We just have a notion of a sea of glue, if you like. So there's no individual gluon here. There's just a glue field, and we're trying to find important configurations of the glue fields based on the same type of tricks we used for the important configurations of those magnets. So there are definitely approximations here, because of the finite lattice spacing and things and finite box size and et cetera. But they're completely different from the perturbative approach.
Okay, but how exactly do you go about importance sampling then if you just deal with the integrals? So for example, it is kind of easy to see with the Ising model that at low temperatures a very likely state would be everything aligned, and at high temperatures a very likely state would be, well, things not aligned. Yeah. But sort of in the lattice QCD thing, what would a likely state for the glue field look like?
Well, exactly. Yeah, we don't know, but because degrees of freedom are complicated. But when we talk about likelihood, then we're talking, it happens, all this rests on the fact that the integrand can be interpreted as a probability distribution function. So, so when I slipped in that probability in the Ising discussion, okay, the integrand of my sum is related to this term. Now I've suppressed the dependence on the spin up and spin down because they're either +1, the product is either +1 or -1. But inside here, I can turn this into a probability distribution function that tells me how likely any given configuration is at a given temperature. And it's I don't want to go too technical, but it's exponential, so it's very sharply peaked. So it's not a Gaussian distribution. Well, yeah, sorry, it's called a Boltzmann distribution. So it's very sharply peaked, and the states that contribute significantly to the integrand are a small number. I don't know if that answers you. And so we do the same thing in QCD. We have some really long expression. We have some energy functional of the fields, that builds in a sort of a kinetic energy term. In classical terms, you might think about how bendy a classical field is. That's like a kinetic energy term, and then the term, bringing in the strength of the interactions. And so the method relies on being able to, calculate the probability, the likelihood of seeing that configuration for the various parameters that you put in. And maybe even more, I mean, you're not comparing that probability to an overall probability, but you're comparing relative probabilities. You're saying, I start with some random configuration. Now I go in and I tweak some numbers. Have I made a configuration that's more or less likely? If it's more likely, then I accept it into my ensemble and go on. Otherwise, I might reject it. A bit like a complicated version of the majority rule. But it is probabilistic, and we're not making guesses. We have a quantitative expression that I'm not showing you that allows us to turn our integral into something that we can interpret as a sum over probability, over a probability distribution function. Sorry if that was too much jargon.
Oh, no, I think it was quite illuminating. Thank you very much, and great talk overall.
Thank you.
There are a few questions in the chat, so I'll read them. Could you explain again how the correlation length is connected to the hadron mass?
I could try. Yes, so it's a... Did I have a nice picture? Not really. Well, here's the statement, yeah. So, well, the correlation length, as I said, if we, what do I want to say? The correlation length actually comes into the correlation function I told you about, sort of with my fingers, right? So you see how correlated things are as you move two spins to magnets away, right? So you would look at this product of two spins at one distance, another distance, at ever increasing distances. Let's call that distance r. Now, that product should decrease exponentially in the function e to the minus r, but r has some length dimensions, so you have to divide by another length, and that's called the correlation length. So if your separation is smaller than the correlation length, then e to the minus something small is, not too much smaller than 1. But if r gets much bigger than the correlation length, then r divided by the correlation length is large, and e to the minus r over your correlation length is small. So by looking at these, how correlated pairs of magnets are as you get farther and farther away, you can fit that to some exponential curve, decaying exponentially, and r is your variable, and so you fit it and you figure out the correlation function. The reason I wanted to connect that to the mathematics is that we turn that r over the correlation length into a distance times a mass, right? So in the units we're working with, a mass has dimensions, an inverse mass has the dimensions of length. I'm sort of setting the various constants equal to 1, the speed of light and Planck's constant. And also I want to, in QCD, I want to measure that correlation function in my Euclidean time. Okay, sorry, this answer is really for people who have had some physics, but right, so what I'm measuring is a correlation function in Euclidean time that should decay like e to the minus m times time, right? Now that should resonate a little bit. If you remember that I told you that I'm working in imaginary time, I'm looking at an energy, e to the minus energy, the mass in energy units times the time. If I go back to real time, that's an e to the I times energy times time. And that's our quantum time evolution operator. So I'm ignoring details, but basically if we look at the bound state in QCD, that doesn't have any kinetic energy, it just has energy due to due to the fact that quarks are bound inside of it. It's got some mass, and so the exponential fall off in Euclidean, or rather imaginary time, is governed by this mass. Rather, it's essentially the inverse correlation length. Yeah, and it's connected to how things propagate in quantum mechanics in time. So how things evolve in time. So in normal quantum mechanics, non-relativistic quantum mechanics that you would have seen, that the time evolution operator is e to the minus I times the Hamiltonian times time divided by h bar. And so we've set h bar equal to 1. We've taken I times t and made that into real. And so so basically that's the connection. You have to go to this imaginary time to get real exponentials. That also is connected to the previous question about probability distributions, so that we get real exponentials that we can interpret as probabilities, rather than e to the i's, these complex phases that appear normally in quantum mechanics in real time. So that's the connection. I should probably, well, I don't think I tried earlier, and it's impossible to read things on the board anyway, but so that's, again, rather a technical question. So I'm hoping that you've taken, if that's coming from a physicist, that might have answered the question. If not, then I think it's hard to justify beyond that.
Thank you.
Mm-hmm.
The next question is there any underlying mechanism which prevents +1 third and -2 thirds charge combinations?
Why? I can't think of any. Yeah, I mean the plus and minus are arbitrary anyway, but if there is I'm failing to think of it. I think I mean certainly things would be different, but I don't think they would be inconsistent. Yeah. Yep. It's a good question. I think probably could cook up a world where that worked.
I have a further question. You mentioned imaginary time. Why is imaginary time useful in the case of physics, or in the case of, I guess, QCD?
Yeah, so yeah, I sort of said it too quick, but in my previous answer about the importance sampling, the reason why we can use this importance sampling is because we want to interpret the integrand as a probability distribution. So probabilities need to be between 0 and 1 once they've been normalized. And they shouldn't be, in particular, they shouldn't be complex. Which we do. So when we write down the integrals that we need for QCD, in real time, in the, time that we live in and space, then those integrals are multiplied by oscillating phases. Actually, it's those phases that give us the interesting interference patterns that we see in quantum mechanics. If you've seen discussions about Feynman's, way of looking at quantum mechanics, where the famous double slit experiment is described, a single electron actually goes through both slits and it interferes with itself. And so somehow his way of describing that is that, electrons go through, an electron actually travels every possible path, or you have to add up all the possible paths that the electron goes through, weighted by e to the I times the classical action. And so those phases are what give you the interference of the electron with itself. So the real quantum mechanics has these complex phases, and just numerically integrating, something that's very wiggly is very difficult, because there's so many cancellations. So but if we make the trick of taking, sort of continuing in the complex plane from real time to imaginary time, then all those integrals become real, and the oscillating phases become quickly decaying exponentials, and it's very good for importance sampling. Now that continuation from real time to imaginary time can only be done, mathematically, if there are no weirdnesses in the complex plane, no singularities, no poles and things. And for the kinds of questions I'm interested in, or that I'm able to answer, involving just hadron masses and simple decays where there's a single hadron in the initial state and a single hadron in the final state, that switching between imaginary time and real time is benign. Everything is nicely connected mathematically in what we call the complex time plane. But there are questions we definitely can't answer that naive way. Because in nature, things do decay. A hadron might decay to 2 hadrons. Kaon will decay to 2 pions. That is not something we can describe using these naive methods. This straightforward methods that I've touched on now. A much more complicated framework is needed. And that's current research. Well, it's been ongoing for a while, but I think that's an exciting direction. But it definitely requires a much more complicated framework to connect the imaginary time theory to the real theory. It's not straightforward.
Thank you very much.
Yep.
Perhaps, Dr. Wingate, how much time do you have?
I think probably 10 minutes.
Okay, because there are 3 more questions in the chat. So
okay.
Maybe 2 questions are related to CKM matrix, so maybe I can connect them to one question. So, does the CKM matrix emerge naturally from the theory? And how does the Higgs mechanism link to the CKM matrix elements?
Right, there is another slide, but it's for a different talk but I don't think I can find it too quickly. But so yes, yes, this matrix is a consequence of the Higgs mechanism, and it's sort of generic. It's what you would expect. So when we write down the theory without symmetry breaking, so if we write down the weak theory in just the way that we would write down QCD or QED, then quarks are bundled together in these so-called doublets, weak doublets, one up, one down, one up type and one down type, and they're massless, right? And the W bosons are massless, and so that's and in fact, it brings in the electric theory as well. So it's the full electroweak theory. Now the Higgs mechanism, or Anderson-Higgs, I mean, the mechanisms, was understood by many people, breaks that gauge symmetry. And right, and so then you write down terms that sort of decouple these 2 things. Yeah, basically you have to give a mass to the W bosons, and the coupling of, basically it gives you a coupling between the quarks and the Higgs field. And that doesn't necessarily have to come in the same, basis here, okay? These doublets are really electroweak doublets, and if the symmetry is broken, then there can be mixing between these elements. So if we had, so to say another way, if the symmetry were respected, then U quarks would only change to D quarks, C quarks would only change to S quarks, and so on. But the symmetry breaking can happen. I mean, it's a sort of spontaneous thing. It doesn't have to be perfectly aligned with these doublets, and in fact, it's not. So the partner of the U is actually not the down quark that we see propagating in the neutron, for example. It's a mixture of the down. So yeah, so we would look at the down quark that's coupled to the U quark, but it's actually it's mostly, because VUD is large, it's mostly the down quark that is propagating in the neutron. But there's some mixture of a strange quark in that coupling. So it's possible to measure a U, well, sorry, I've got the masses around, you wouldn't do it, it would go the other way. You'd measure a strange quark decaying to a U quark, so going from this way to that way. So I think it's generic, it's I would say it naturally comes out of this symmetry breaking. What's unexpected is anything to do with the structure of this matrix. I mean, it turns out to be quite close to diagonal, but there's no reason why it should be. Something similar may be happening with neutrinos, and the mixing matrix there is not anywhere near diagonal. So there are questions. There are a number of free parameters here. There are some properties this matrix has to satisfy, namely unitarity, and then there's some other arbitrary things we can rotate away. So there are only 4 free parameters here, but they're really free as far as the theory is concerned. We need experiments to tell us what they are if the standard model is correct. And the hope is that if we do enough measurements, actually 4 free parameters won't, no single set of 4 parameter values will describe all experiments. And that will mean that some measurements being affected by something outside of this framework, something outside the standard model. Yeah, so that's sort of what's described there. I don't know if that answered the questions.
Okay, thank you. And the last question, it's a bit longer. So in the simulation program for the Ising model, instead of studying how the number of spin up and down, their distribution evolves with temperature, why we don't consider the ensemble of the spins up or down as a geometrical object? Then, by using a box counting algorithm, we can study how the fractal dimensions of these geometrical objects, ensemble of blue boxes or yellow boxes, evolves with temperature. So we can have another way to study the same phenomenon by a more geometrical approach.
That may be interesting. I think it's an interesting idea. I haven't thought of that, sort of looking at sort of the fractal nature of the boundaries. But so one of the nice things about these models, and something we rely on when we take the so-called continuum limit, is this something called universality. And and that's exciting just in these statistical systems as well. It turns out that the way that we go to critical temperatures and the way that these correlation lengths scale with temperature. So if I get close to the critical temperature, yeah, just for picture's sake. Yeah, so going around, right, as the correlation length is getting larger here, the details, so the way that it goes and the scaling that it behaves, actually, you can find numerically very similar results, in fact, equal results for a wide variety of statistical systems. So independent of the short distance details. So for example, if I were to replace this square lattice with a triangular lattice, put a bunch of triangles there, equilateral triangles, and so then every neighbor would have, I suppose, 6 nearest neighbors. That's a different geometry, but the large scale, what's happening to these large blobs and the way that the correlation function is going to infinity, essentially, as the temperature gets closer to the critical temperature, will be the same, governed by the same large scale universal physics. So that's the most exciting thing about this kind of phenomena, is this kind of universality that a lot of different microscopic physics will yield the same critical phenomena. And we rely on that in the lattice calculation, actually. Because we're discretizing our theory of quarks. We're replacing real derivatives by finite difference operators, and there's no unique way of doing that. so different people can make different choices. And we're relying on the fact that the details of that won't matter as we make the physical length scales large compared to our microscopic artificial, in that case, lattice scale. So I think it may be an interesting geometry question, or interesting way to discuss these shapes. I'm not sure. Yeah, I haven't thought about it, probably just because it doesn't overlap with my particular interests in these theories. But there are, yeah, people are interested in sort of domain structures and boundaries between domains, but could be something there.
Okay. Thank you.
Okay.
And Dr. Wingate, many thanks for your great talk and answering the questions.
Thanks very much. It was a pleasure to talk with you, and it was nice to have so many specific and interesting questions. So yeah, it's really nice forum to speak. Thank you.
In the peak, we had 60 participants.
Oh, wow. Okay, great.
So,
Good. Well, have a good break, everyone.
Yeah, thank you. So this was the last TCSS event of this term, and I hope to see you in the Lent term again. Thank you for attending the talk. Have a nice Christmas break and stay negative. Good. So, bye.